Welcome to our video on data transmission across a network. Today, we'll embark on a journey with an HTTP request exploring how it travels from a client to a server, through various network layers and routers and back to the client. Let's dive into the intricate processes involved in this essential communication. Imagine you are a user wanting to access a website. To do this, your computer, referred to as the client, needs to send an HTTP request to a remote server hosting the web page. But how does this request navigate the complex landscape of networks and routers? In this video, we will break down each step of the process, revealing the technology and protocols that make it all possible. The journey begins when the client sends an HTTP request to the server. This request includes various elements such as the method, like get or post, the URL of the requested resource, and additional headers. The client prepares the request for transmission, ready to enter the world of networking. Before the HTTP request can be sent, it is broken down into smaller, manageable pieces known as segments by the Transmission Control Protocol or TCP. This segmentation is crucial as it allows large amounts of data to be sent efficiently and fit within network constraints. TCP ensures that even large files can be transmitted smoothly without overwhelming the network. Each segment is generated by TCP is encapsulated with a TCP header. This header contains essential information such as sequence numbers, which help keep track of the order of segments, and acknowledgement numbers, which confirm the receipt of data. This added layer of information is vital for maintaining the reliability of the connection. Once the TCP header is added, the segment is handed over to the network layer, where the IP header is appended. This header includes the source and the destination IP addresses, effectively guiding the packet through the network. The destination IP address is critical as it tells each router in the path where the packet is ultimately heading. It's important to note that the size of these segments is designed to be smaller than the maximum transmission units or MTUs. Now, as we move into the data link layer, we see the Ethernet header being formed. The Ethernet header contains fields such as the source MAC address. This would be the MAC address of the server. However, the destination MAC address remains unknown at this point, represented by a question mark in our diagram. To send the packet to the next hop, the server needs to know the MAC address of R1, the first router in the path. This is where the Address Resolution Protocol or ARP comes into play. ARP helps resolve this issue by broadcasting a request across the local network as who has the IP address of router 1. Router 1, often called R1, receives the ARP request and promptly responds with an ARP reply, providing its MAC address. This response ensures that the server can send the packet to the correct next hop, R1. This exchange of ARP messages is essential for the proper functioning of local area networks. To optimize the process, R1 maintains an ARP cache, a temporary storage of recently resolved MAC addresses. This cache helps reduce the number of ARP requests sent over the network, thus minimizing unnecessary traffic and improving communication efficiency. With the MAC address determined, an Ethernet header is added to the packet. This header is vital for frame transmission over Ethernet networks and include information such as the source and the destination MAC addresses. This prepares the packet for transmission over the local network. Upon receiving the packet, R1 analyzes its contents and decides the best path to forward it. This decision is based on various factors, including its routing table, which contains information about the best routes to different networks, as well as considerations like network congestions and link reliability. If R1 needs to determine the MAC address of the next hop, which could be router 2, it sends out another ARP request. This process is repeated at each router along the path until the packet reaches its destination. Router 2 receives the ARP request and sends back an ARP reply with its MAC address, allowing R1 to encapsulate the packet for the next hop. This ARP exchange continues as the packet moves through subsequent routers R3, R4, and so on until it reaches router 8, the final router before arriving at the client. Once the packets have successfully traversed through R8, they are almost at the client. However, R8 still needs to deliver the packets to the client, and for that it requires the client's MAC address. Since R8 only knows the client's IP address at this point, it sends an ARP request to the local network asking who has the IP address 192.168.5.10. The client receives the ARP request from R8. Recognizing that the request is for itself, the client prepares an ARP reply and sends back a message directly to R8 with the MAC address. With the packets arrived at the client begins to process the data it has received. Upon receiving the segments, the TCP layer in the client acknowledges the successful delivery of the segments. Once all segments are received, the client begins the process of decapsulation. Each layer removes its respective header one by one. Starting from the data link layer, the Ethernet header is stripped off, followed by IP header, until only the original HTTP request remains. Finally, in the transport layer, the segments are arranged according to their sequence numbers. This step is crucial for reconstructing the full image or HTTP response that the client initially requested. Once arranged, the complete data is presented to the application layer for further processing. In summary, we've taken a comprehensive journey through the various stages of data transmission from client to a server. We explored the roles of TCP, ARP, and routers and how the client handles missing packets. Understanding this process is essential for grasping how data communication occurs over networks, and it highlights the intricate mechanisms that ensure reliable communication. Thanks for watching.